All right, chemistry, this is your video lecture for chapter 7, section 3. We're going to start using chemical formulas. We're going to get some information out of these things. One thing that we want to have a basis for is calculating formula mass. The definition is in your book. We'll be going over that in class. But a formula mass is related to the molar mass of a compound. Now, the molar mass of a compound is the mass of the atomic mass units for one molecule. It's the same number, the same numerical value, but it's on a much different scale because the units are different. Formula mass takes into consideration the number of atoms of each element in a compound. So when you look at the formula for, say, NaCl, the formula mass takes into account that there's only one of each kind of atom. There's a total of 2 atoms there. Formula mass is also calculated the same way as molar mass, except we measure using AMU, atomic mass units, instead of grams per mole, which is the unit for molar mass. So let's try a practice right here. You're going to use the same procedure for calculating the molar mass of a particular compound. In this example, it's going to be magnesium carbonate, but instead of having grams per mole as your unit, you're going to have AMU. Go ahead and pause the video and see if you can do this. This was a few chapters back. Let's see if we can still do it. All right, see how we did. Now there's magnesium. Now, depending on what the periodic table you're using, you're going to see these 3 elements as having some differing number of significant figures. That's not important. Let's just pay attention to the procedure. You'll be using the values that you have on your periodic table. Do we see that there's 1 magnesium atom, there's 1 carbon atom, and there are 3 oxygen atoms. So we have to adjust for the fact that there's 1 magnesium, 1 carbon, and 3 oxygens. And so we'll set up a calculation where we use the mass of 1 magnesium atom, the mass of 1 carbon atom, and the mass of 3 oxygen atoms. That's why we're multiplying 16 by 3. Carry out that multiplication first as per your order of operations, and then add those 3 values together. Come up with 84.32 AMU. And at this point, I'd like to plug significant figures one more time. Notice that the very last function that we're carrying out is addition, and so the significant figure rule we're using there is however many decimal places past the decimal point we are included in the value with the fewest digits past the decimal point, that's the number we use. But in this case, every single value that we're using here has two figures past the decimal point, so our answer, the 84.32, will have 2 figures past the decimal point. All right, look like I got some fun formatting issues here. The molar mass is the mass of 1 mole of a pure substance, just that substance, nothing else. 1 mole of it, the mass of that 1 mole is what we call molar mass. For example, the molar mass of iron is 55.847. On your periodic table, I believe it reads 55.85. That's fine, that's just 4 significant figures. Now, I'd intended to give you an atom and ask you to use your periodic table to figure out the molar mass, but I guess we'll do this Jeopardy style. Here, the answer is 195.08 grams per mole. This is the element that has a molar mass of 195.08 grams per mole. Ready, go. All right. The correct response is, what is the molar mass of platinum? Right? If you look at your periodic table, you see for iron, you're going to see that 55.85 value. You're also going to see for platinum the 195.08 value, or maybe a 195.1 value. That's just depending on the number of significant figures used. Now, the molar masses depend on the particles that compose that compound. So if your element exists as a molecule, i.e. Brinkelhoff, the diatomic molecules, if you're going to calculate the molar mass of that molecule, the mass is going to be 2 moles of that element. For example, oxygen. I'd like you to try this right now. Go ahead and press pause. You're going to take the mass of one oxygen atom, or the molar mass of one oxygen atom, and try to correct for the fact that one molecule of oxygen has 2 atoms per molecule. Go ahead and press pause and see if you can carry out that function now. All right, using your periodic table, you're going to see that the mass of oxygen is 16.00 grams per mole. Well, oxygen, the molecule, has 2 atoms, so we have to double that. We'll get up to 32.00 grams per mole. The molar mass of oxygen molecules is twice the molar mass of oxygen atoms. So remember that for any of those Brinkelhoff elements, Brinkelhoff, right? Those 7, bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine. Remember those. All right, so here's a list, protocol, instructions for calculating the molar mass. First, list the elements. Figure out exactly what elements you have in that compound, and then determine how many of said atom you have. Figure out the atomic masses of each of those elements. Simply use your periodic table, and then multiply how many atoms you have by their respective atomic masses. Once you've done that, add up the totals. All right, I have some practice problems for you. With some interesting formatting issues I didn't realize were there. First one I'd like you to try, I'd like you to calculate the, actually, I'm sorry, I'll do this one. I'll do H2O. So H2O, I'm going to list the different kinds of elements I have. I have hydrogen and oxygen. So I'll start with hydrogen. There's 2 hydrogens here. I'll use the periodic table to see the mass is 1.008 per atom. There are 2 of them, so I'm going to multiply it by 2. And so the mass due to hydrogen is going to be 2.016. There's 1 oxygen at 15.99. 15.99. I'm going to add those together. I'll get 18.006. Now again, the periodic table that you have for this class might show fewer significant figures. That's no big deal. You just use those values specifically. All right, I'll try one more, and then I'll have you guys try the next 2. NaCl. I have some sodium. I have some chlorine. How much sodium do I have? I have 1. Look at the periodic table. I see that the molar mass is 22.9 grams per mole times 1. It says 22.9. Look at my chlorine. There's 1 of them as well. The periodic table tells me that the mass of chlorine is 35.45 grams per mole. Add those up. Come up with 58.35 grams per mole. All right, I would like you guys to press pause and try to calculate the molar mass of C6H12O6, also known as glucose. Please press pause now. Let's see how we did. Carbons, there's 6 of them. The periodic table tells me that there's 12.01 grams per mole of carbon. Multiply by 6, you get 72.06. Hydrogen, periodic table tells me 1.008 grams per mole. There are 12 of them, so multiply by 12. You have 12.096. Oxygens, periodic table tells me it's 15.99 grams per mole. There are 6 oxygens, so I'll multiply that by 6. Let's sum those, and I have 180.096 grams per mole. One more for you to try. Try K2O, potassium oxide. Please press pause now. All right, let's see how we did. Potassium, periodic table tells me the mass is 39.1 grams per mole. There are 2 atoms of potassium here, so I'll multiply that by 2 to get 78.2. The oxygens at 15.99, there's 1 of them, so that goes straight across. Let's add those together, and I'll end up with 94.19 grams per mole. All right, let's talk about the mole here. We're going to take those molar masses, and we're going to convert from molar mass to formula mass to a number of things. And one of the things we're going to need to do is take a molar mass and convert into a number of molecules of that substance present. Okay, so we're going to need this concept of the mole. And this is going to be a little bit of a refresher. So hopefully this is somewhat familiar. A mole is simply a convenient unit to use when we're talking about huge numbers of things. A mole is a unit. It's anything. Any kind of object, anything you could possibly want to count. As long as there's 6.022 times 10 to the 23rd of those things, that is a mole. You have a mole of cars, you can have a mole of buildings, you can have a mole of dollars, you can have a mole of atoms, you can have a mole of particles, you can have a mole of compounds, whatever it is. As long as there's 6.022 times 10 to the 23rd of them, that's a mole. Same thing as saying there's a dozen or a gaggle or something like that. Or is a gag? No, I'm sorry. Google. Yes. Now, again, the reason that the mole is useful is because atoms are so small and it takes so many of them to accomplish any meaningful amount of matter that this huge number is useful. Okay, we need this many atoms to actually be large enough for humans to interact with. So it's a fairly arbitrary number. It's just something that is useful for humans. Again, 6.022 times 10 to the 23rd particles in 1 mole. We call this number Avogadro's number because he was actually investigating this at the time of his death, essentially. And so it's named in honor of him. Using the periodic table, you can find the average atomic mass in AMU of one atom, or the mass of 1 mole of the element in grams. Okay, that's the average average mass that's listed on the periodic table. So you'll always have access to this information because you'll always have your periodic table with you on quizzes or tests or whatever. Avogadro's number, what that 6.022 times 10 to the 23rd does for you is it provides a connecting relationship between molar masses and atomic masses. And so, let's try this. How many molecules of bromine are present in 0.045 moles of bromine gas? Okay. Now, given, what does the question tell us? There are 0.045 moles of Br2. Again, how do I know it's Br2? Because Brinkelhoff, that's a diatomic molecule. So bromine is going to exist as Br2, not just Br. So I have a number of moles, and I want to get the number of molecules of Br2. And like we just said in the previous slide, Avogadro's number is going to be that thing that allows me to go from the moles to the number of molecules. And if you remember their statement of equality here, 1 mole of bromine, and again, it can be 1 mole of anything, it's just for this particular example, it's bromine. 1 mole of bromine equals 6.022 times 10 to the 23rd molecules of bromine. So I can use that statement of equality to create conversion factors. And these are the two versions of these conversion factors I can have. I can either be converting away from moles to molecules, or I can be converting 2 moles from molecules. And all you have to do is flip numerator and denominator so that those units will cancel. Now, for this particular question, this particular problem, I'm thinking since we've been given moles, we're going to want moles to cancel. So I'm going to want something that has moles of Br on the denominator. So this one looks good to me. Let's set up the problem. So start with 0.045 moles of bromine. We're going to multiply that by, again, the conversion factor. This conversion factor is equal to 1 because both of those values are equal to one another. Right, it's just like multiplying a value by 1. It doesn't change the value, but we do get to change the units, which is helpful. So moles of bromine will cancel. The only unit I'll have left is molecules of bromine. All that's left is to throw those two numbers into my calculator, and I'll come up with 2.7 times 10 to the 22nd molecules of bromine. Now, we'll have plenty of time to practice in class how to deal with those exponents. Again, we haven't dealt with them in a few chapters, and so we'll deal with that in class. I'll remind you of the procedure of how to deal with those exponents, but right now I want you to get comfortable with those conversion factors and canceling units. There's one more thing we're going to cover in this section is percent composition. So I might give you that magnesium carbonate like we looked at earlier, and I might want to know what percentage of the total compound is due to magnesium or due to carbon or due to oxygen. I want you to break it down into what it's made of. First step is I'm going to calculate the mass of magnesium carbonate. So I'm going to use what I did earlier in the slideshow, earlier in the notes, and I'm going to take that the mass of magnesium, mass of carbon, and then the mass of 3 oxygens, sum those together, and I'll have 84.32 AMU. So the total compound has a mass of 84.32. Well, if we want to calculate the percent due to magnesium, I'll simply take the mass due to magnesium, divide by the total mass, multiply it by 100%, and I'll have my percent composition. You can do the same thing for carbon. This, instead of the 24.31, we'll divide 12.01 by 84.32, multiply by 1, so we can have a percentage. And then lastly, for oxygen, again, we're going to take 16 times 3, so 48 divided by 84.32, because there are 3 oxygens. Multiply it by 100, so you can have a percentage, and the percentage of oxygen is 56.93. And so what we can conclude from these calculations is a little less than a third of this compound is magnesium, okay? And something like an eighth of this compound is carbon, and then over half is oxygen, okay? So we have 56.93% of magnesium carbonate is oxygen. That's what we're able to say or claim using this calculation. All right, I hope you took good notes. Rewatch this if you'd like. Be sure to read section 3 before the next time you come to class, and bring questions with you. We'll spend time working in class on these problems, but you won't get as much out of it unless you come prepared. All right, I will see you next period.